Ever pondered how a machine comprehends the complex relationships within a sentence? The Attention is All You Need architecture by Ashish Vaswani and others is a revolutionary architecture that replaces traditional sequence-to-sequence models with a self-attention mechanism for machine translation tasks. It has achieved state-of-the-art results in machine translation and other language processing tasks. Well, the magic lies within the transformer model's unique mechanism. In the context of the transformer model, attention refers to the mechanism that allows the model to dynamically focus on different parts of the input sequence when performing a task. Empirically, attention quantifies the importance or relevance of each token's contribution to the output. It's not just about positional importance, but also about how each token relates to others for a given task. For example, how a word in a sentence affects the meaning of the next word in translation. This mechanism assigns a weight to each token, indicating its relevance, and these weights are learned during training. Thus, attention can be interpreted as the model's way of deciding which parts of the input are most relevant for generating the correct output at each step, dynamically adjusting its focus based on the context provided by the input sequence and its positional encodings, which uses the concepts of, or as we like to call them, Q, K, and V. So, in transformers, the query prompt is the information that is being looked for. The key is the in what context or reference, and the value refers to the anticipated content that is being searched. The query and the key are multiplied together to produce the attention scores, which are then used to compute the weighted sum of the values. Let's consider a simple sentence. The cat, which sat on the mat, which was in the house, which was on the street, was hungry. The initial step involves breaking down the sentence into individual words. This process is known as tokenization. Each word, or token, is then converted into a numerical representation using what we call word embeddings. These embeddings encapsulate the semantic meaning of each word. Next, we create 3 vectors for each word: query, Q, key, K, and value, V. These vectors, typically of the same size, are randomly initialized during training. Now, let's calculate the attention score for a particular word. For instance, let's consider the word cat. We begin by multiplying the query vector of cat with the key vector of each word in the sentence. This process results in a vector of attention scores that highlight the relevance of each word to cat. To ensure stability in our computation, we scale down these scores by dividing them by the square root of the dimension of the Q and K vectors. We then convert these scaled scores into probabilities using the softmax function. This ensures they sum to 1, and the resulting vector represents the relative importance of each word in the sentence to cat. Now, for the final step, the weighted sum of values. We multiply the attention score for each word with its corresponding value vector and sum these vectors together. This weighted sum represents the contextually relevant information for cat based on the other words in the sentence. Take, for example, the word hungry. If the attention score for hungry is significantly higher compared to other words due to its semantic connection to cat, the weighted sum will be heavily influenced by the value vector of hungry. This provides context about the cat being the one who is hungry. Of course, this is a simplified example. The actual calculations in the transformer model are much more complex, but it provides a basic understanding of how Q, K, and V work in the attention mechanism. By performing this computation for all words in the sentence, the transformer model can understand the relationships between words, and more importantly, capture the overall meaning of the sentence. So the next time you marvel at a machine's ability to understand language, remember the concepts of Q, K, and V. So in transformers, the query is the information that is being looked for. The key is the context or reference, and the value is the content that is being searched. The query and the key are multiplied together to produce the attention scores, which are then used to compute the weighted sum of the values. The attention mechanism plays a crucial role in focusing the model on semantically relevant data, which can indeed help reduce hallucinations or errors where the model might otherwise generate irrelevant or incorrect output. by dynamically adjusting which parts of the input sequence are most important for predicting each part of the output. The attention mechanism helps ensure that the model's predictions are grounded in the input data, reducing the likelihood of generating nonsensical or unrelated text. This capability is particularly important in complex tasks like language translation or content generation, where understanding context and maintaining semantic coherence are essential.